Let's look at what we mean by a group being a orthopara-director or a meta-director. This table 16-1 on page 494 of your textbook summarizes this nicely. We have over here on the left side, well, first of all, this is all relative, these numbers here are relative rates of reaction adding a nitro group onto benzene, or benzene where there is some sort of substituent that's already attached onto the ring. And so we know that if that substituent is a electron donating substituent by resonance, then it's going to be an orthopara-director, and if it's a meta-director by resonance, then it's going to, or if it's a electron withdrawing group by resonance, then it's going to be a meta-director. And so here is a list of a bunch of meta-directors. They're strong deactivators, and all of them except the first one have a multiple bond between atom number 1 and number 2, as you're used to seeing. Most of these are condensed forms of carbonyl compounds. This one is a nitro group here, and this is a nitrile, but the acid, the ester, the ketone, and the aldehyde here are all carbonyl compounds. So these are meta-directors, and so what we can see here is then when the nitro group adds, somewhere between 66% and 91% of it goes, the electrophile coming in goes to the meta position in relation to this group that is already on here. So it really depends on the particular group that we have on there. The nitro group here seems to be the most successful in directing it into the meta position. 91% of it goes into the meta position, 7% into the ortho position, and 2% into the para position. Other ones aren't quite so successful, 66%. So if you have an ester on there and you want to add a nitro group on there, a majority goes to the meta position, but you still have 28% that is going ortho and 6% that is going para. So you have a lot of material that you would have to separate out to purify the final product, and that's exactly what you need to do. If we go over here and look at the halogens, these are orthopara-directors, as we said. They're actually deactivators, slight deactivators because of the inductive effect. And you see that very little of the material is going into the meta position. So 1% is going to the meta position, 99% is going into the ortho and para positions. But still, I mean, you have a mixture, and you have to deal with that mixture. And so it's interesting to look at the various halogens and see the relative percentages that are going into the various positions. And so there's the deactivators that are orthopara-directors, and then here are the activators that are orthopara-directors. And the methyl group, we'll have to talk more about that, or any alkyl group, we'll have to talk more about that, because that's not, there's no resonance involved. And so our explanation for things being orthopara-directors was based on resonance. And so here, if there's a hydroxy group on there, which we've talked about already, you have 50% of it will go ortho and 50% of it will go para. When you have a bigger group here, this is an amide group, NH, carbonyl, and methyl group. When you have a more bulky group, what happens? You don't see nearly as much ortho product, and you see a lot more para product. So this branching that is occurring here on this substituent slows down, crowds the ortho position, and then favors the para position. So I just wanted to point out to you on this this table, when we say something is an ortho-para director, we don't mean there is no meta. I mean, there's hardly any meta there. When we say something is a meta director, we see that there's a fair amount, often a fair amount of contaminant that is coming from the ortho and the para products. Okay? So we're just talking about the major products. And you should just have a general sense that in the balance between ortho and para, if there's crowding stuff going on, that minimizes the ortho. The other thing you should think about when we're competing here for the ortho positions and the para, and you've probably already thought about that, is that there's twice as many spots for it to add ortho as para. So statistically, you should have, if you're adding an electrophile, you should have twice as much of it adding ortho as para, but there's always this little bit of crowding interaction, and sometimes it's a lot more that minimizes the amount of ortho there. So the other thing that these substituents are doing on the ring is they're speeding up the process of electrophilic aromatic substitution, or they're slowing it down. And so what I wanted to point out here at the top of the page, 494, is this relative reactivity. We talk about things being activators or deactivators. So if we have just plain benzene and we have a rate for it, the rate of adding a nitro group, we call that 1. Okay, so just for purposes of comparison. And then if we put a hydroxy group on the ring, then the nitro group will add 1,000 times faster. And so it's very much speeding up. It's activating. It's a strong activator. It's activating the ring. If we have another orthopara director, the chlorine, which we've already said is a weak deactivator, then it is 3/100ths the rate of just plain benzene. And if we have one of these nitro or electron withdrawing groups that are strong deactivators with a pi bond between the first and second atom, like the nitro group, this is probably one of the extreme examples, but 6 times 10 to the negative 8th. Remember that 10 to the 6 is a million, so we're talking about a huge difference here in the rate, somewhere between 10 and 100 million times slower than the benzene ring by itself. Okay, so that just gives you, again, an idea of the magnitude of the activating effect and the deactivating effect of a couple of the groups. So in the next video, we're going to look at the mechanism of, or we're going to actually draw out an energy diagram of the mechanism of electrophilic aromatic substitution, and we're going to look at how your book has explained on pages 499 to 502 the ortho and para and meta directing effects of substituents that are already on the ring. And we'll use that to discuss down here at the bottom, to discuss how the methyl group, even though there's no resonance, how that could possibly be an ortho-para director.